This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 3, Lesson 8, Refrigerant Line Sizing. Like the insulation section, this one is table-driven, not formula-driven. The handbook prints line capacity tables in tons for the suction, discharge, and liquid lines of R22, R134A, and ammonia. The only equation is a scaling correction that adjusts a table capacity to your actual equivalent length. We'll read the table, scale it once, and flag the traps that make these problems bite. First, know what this section is. For each halocarbon refrigerant, the handbook prints 3 capacity tables: suction, discharge, and liquid, 1 per line in the system. You enter with the line size and the saturated suction temperature, and read a capacity in tons. There is no Darcy pressure drop calculation on these pages. The friction work is already baked into the table. The same 3-table structure repeats for R22, R134A, and ammonia. The only math is a scaling correction. Each table is built for 100 feet of equivalent length and a fixed saturation temperature penalty. Your real line differs, so you scale. The capacity form raises the length and penalty bracket to the 0.55 power. The penalty form raises its bracket to the 1.8. 2 independent tools for 2 questions. And watch the key term. Delta T here is not a temperature difference across a coil. It's the friction pressure drop written as an equivalent drop in saturation temperature. The tables also assume a 105-degree condensing temperature. The problem: a single-stage R22 system runs at 40 degrees saturated suction, 105 condensing. For a 2.5-inch Type L copper suction line, the table reads 33.1 tons at its 100-foot 2-degree basis. But the real run is 100 feet of pipe plus fittings and valves worth another 50 feet of equivalent length, and you hold the same 2-degree penalty. So the line can't carry the full table capacity. Scale it down to the real equivalent length. Solve. The length ratio is 100 over 150, about 0.67. The penalty ratio is 1, since we held delta T equal. Raise the bracket to the 0.55 power and multiply by 33.1, about 26.5 tons, so the extra 50 feet of equivalent length cuts the usable capacity from 33 down to roughly 26.5. If the load is bigger than that, step up a size and read again. Notice the exponent softens the hit. A 50% longer run costs only about 20% of capacity. There's a second tool for the reverse question. When the line size and the load are both fixed, and you want the resulting penalty, use the 1.8 form. It tells you the saturation temperature drop that line and load produce, so you can confirm it stays under what your system tolerates. Too much drop on the suction line starves the compressor. These 2 equations are separate curve fits, so don't run one backward to check the other. Traps. 4 ways this bites. 1. The capacities are in tons of refrigeration, not airflow or gallons per minute. Don't convert. 2. Use equivalent length, the straight pipe plus every fitting and valve, not the bare pipe length. That's the most common miss. 3. The tables assume 105 condensing. At any other condensing temperature, multiply by the correction factor, and it applies to both suction and discharge lines. 4. Delta T is the pressure drop, written as a saturation temperature penalty, not a fluid temperature difference across a coil. Quick recall. Read the right table, suction, discharge, or liquid, entering with line size and saturated suction temperature, and the capacity comes out in tons. Scale it to your real equivalent length with the 0.55 equation, or use the 1.8 form when size and load are fixed and you want the penalty. Correct for condensing temperature off the 105 base. Golden rule: capacity in tons, equivalent length not straight length, and delta T is a saturation temperature penalty. Ammonia and R134A use the same method on their own tables. Next, Lesson 9. Food processing and cold storage loads. You can now size the piping that ties the system together. Next, we find the load it has to remove. We assemble the product cooling load from the handbook's food data: freezing point, specific heat above and below freezing, and latent heat of fusion, into a sensible plus latent plus sensible pull-down. Everything's at peprepengine.com. Cheat sheet, worked solution, and a quiz attached here. If the course helps, subscribe.
The full study guide with every equation and common exam trap is free at peprepengine.com, link in the description. Structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.